Hello, this is Terry Iverson from Champion Now and CNC Rocks. Today I want to talk about grinding, and in particular cylindrical grinding. This is a cylindrical grinder, CNC cylindrical grinder with a FANUC CNC control, which means it's computerized and all the movements are controlled by the computer. This particular machine is made in Switzerland. The Swiss make very high-end, expensive, very accurate equipment in the machine tool world. This particular machine is a cylindrical grinder, and we have a shaft for demonstration purposes, a shaft on there, and you can see that the wheel is spinning. On a grinding machine, you have a stone wheel that actually contacts the metallic surface and does the machining, or in this case, the grinding. Some grinders have an ID attachment, and ID means inner diameter, where the wheel head, where the wheel is located, would rotate, and there would be a spindle that will allow you to do ID grinding with the wheel inside, in an arbor, inside the spindle. In this case, right now, we're going to do a little bit of a cycle and a demonstration of a traverse grind on this shaft. We won't actually be grinding. And you'd never have this door open, by the way. This is not safe. So I just want to, make sure that you know that. I just opened it for demonstration purposes, so you could get a good view of the grinding wheel and the wheel head. On a grinder, you have the work head, the wheel head, and the tailstock, and some people call it the footstock. Remember, a lot of our terms in machining are very literal. So head, headstock, footstock, otherwise known as tailstock. I think you can get the correlation. So basically, one of the things that you'll also note on grinding is that when you come in to do a grind, you need to identify a surface, a shoulder, that you don't want the grinding wheel to touch. Or maybe you do want to grind the face and touch the shoulder, and there's such a thing called flagging. Flagging is a unit that usually has a ruby on the end of it, and it's a sensor that allows the machine and the computer to tell where the edge of the wheel is in relationship to the edge of the shoulder. That's called flagging. One of the other things that you need to understand about a grinding wheel is, in grinding in general, is that when you grind, the wheel wears because of the contact between the metal, usually hardened metal, in a Rockwell C scale, maybe 58 to 62 is very common. And so as the wheel wears, you need to adjust it, and you need to what they call dress it. And dressing a grinding wheel, the stone, is done with a diamond. So either on the back of the work head, or the back of the tailstock, or on the table, you'll actually have a diamond positioned. And remember, diamond is one of the hardest materials known to man. So it can actually machine or dress, as it's called, the stone, the grinding wheel. So you periodically have to dress, and you can make that part of the cycle on a grinder, on a CNC grinder especially. So what I'm going to do is I'm going to cycle start the machine. The wheel's already running. And then we're going to actually see the wheel come in and traverse on the shaft back and forth. Now in grinding, there's such a thing called plunge grinding, where you would come in and plunge either a diameter, maybe the wheel's wider than the diameter you're grinding, so you could plunge that. Or traverse grind, where you have a surface that you want to grind that's much longer and much wider than the grinding wheel. So you would traverse back and forth. And sometimes you would come in to a diameter, traverse across, then go in again and traverse across. There's a number of different ways you could do that. Or you could do a box pattern where you come in a little bit each time. Now in many cases, if you wanted to grind a shoulder, you would have the grinding wheel or the wheel head on an angle. And that would approach on an angle and come in, and you would dress the actual face or the shoulder into the wheel. So that gives you an idea. If you have to do a taper or a contour in grinding, you would use the control to dress the wheel to have that radius or that angle in the wheel so you could actually come in and plunge that detail onto the part. On the CNC control, you'll actually see a manual pulse generator, which is the hand wheel, which means you can position the wheel and the wheel head in such a manner that you can come in and see how close your approach needs to be so you don't actually touch the part prematurely. And grinding machines, CNC grinding machines, use acoustics. It'll actually use an acoustical component so that it can actually hear that it's getting close before it touches the actual piece. So that's a functionality of a CNC grinder. You also have to balance the wheel in grinding. So you have this wheel that's mounted onto a hub. That's the interface between the wheel head and the grinding wheel. It's mounted on a hub. And when it comes from the manufacturer, it isn't always balanced. So you may have run out, and you don't want that when you actually grind a part. So what you'll do is you'll balance it. In some cases, some grinding machines have automatic balancing, where they'll actually rotate and move weights on the hub so that the wheel's balanced. They also have the ability to manually balance, where you put it on a stand, the wheel on a stand on the hub, and you rotate it, and then you position weights on almost like on a clock at 2 o'clock, 10 o'clock, 6 o'clock, and adjust them so that you get a perfect balance. That would be manually balance it. After you balance the wheel and you mount it, and it's on the hub and you mount it on the wheel head, then you'll want to dress it, which trues everything up and makes everything perfect, so to speak. Generally speaking, grinding is usually plus or minus 1/10 and down. Some cases you'll be in microns. Remember, a micron is about 39 millionths. So when people start talking in microns, plus or minus 1 micron, that's plus or minus 39 millionths, 50 millionths for rough guesstimate, which would be a total of a tenth, 1/10,000th of an inch. Just to put everything in perspective, the human hair is about 7 thousandths in diameter. If you take a tenth of that, you have 7 10,000ths. If you take a tenth of that, you have 70 millionths. And if you take half of that, roughly, you have 35 millionths, and a micron is 39 millionths. Just to put that in perspective to the human hair. One of the other things that grinders are known for, cylindrical grinders, is to hold those close tolerances that I mentioned, such as a micron or plus or minus a micron. You will have gauging. And there's different companies that manufacture gauges that actually measure, let's say, the front side of the part while you're grinding the back side of the part. So you actually have a very interactive feedback of what your diameter is, diameter being the size of the part, to as you're machining it, or in this case, grinding it. So that feedback goes back to the control, and when you dwell at a certain location, that you'll come to size, and they call that sparking out. If you dwell the grinding wheel on a part, usually you'll get a spark. And then when you dwell long enough and it gets to size and it's not grinding any longer, it'll actually quit sparking, hence the term spark out. Then you'll retract the wheel. In terms of coolants, sometimes people grind in oil. A lot of cutting tools are ground in oil. And there's pluses and minuses to that, and we'll talk about that. And then sometimes you have more of a water-based or water-soluble coolant. Water-soluble coolants are very damaging to machine tools. Oil coolants are very nice to machine tools. Having said that, there is a potential danger or detriment. When you use oil, that has a flash point. And when you use a grinding wheel, I just said that you have a spark. So, as you could probably well imagine, when you have spark and a flash point and a flammable item like oil, you can actually have a fire. That being said, they have fire suppression systems that are very common on different machine tools, but especially common on grinding machines, cylindrical grinding machines, that use oil coolant. It's a safety so that if in fact the flash point of the oil, the spark, when you spark, the grinding wheel sparks out or sparks on the workpiece, you kind of have a recipe for a fire. So many times what you'll have is fire suppression equipment that will be recommended, very significantly recommended, for a grinding operation. When you have acoustics, I made mention a minute ago about acoustics, that's called gap control. Gap control is if you have the workpiece here and the grinding wheel here and you wrap it in, you want to wrap it to a point where you don't waste time. You don't want to feed all the way from back here, say, all the way up to your part, because that's time, and in machining, time is money. So what you want to do is you'll wrap it, which means in a quick fashion, as you can imagine. You'll wrap it till you get close. And gap control is an acoustic measure so that when it hears that it's close enough to the workpiece, it'll then go into feed rate, into a feed, so that you're not wasting time. Sometimes you'll see grinding, old timers that do grinding, they'll have a little mirror on a retractable stick of sorts. And so they'll use that so they can look to the back side of the part where the wheel is to see how close they're getting the grinding wheel to the piece being ground. Sometimes grinding equipment, cylindrical grinding equipment, some of them will have what they call hydrostatic ways. Hydrostatic ways is a film of oil that's pressurized so that the metal doesn't touch. And so you're actually floating on oil. Those are pretty sophisticated machines that employ that type of design or capability. We talked about in some of the previous videos about heat. Heat is your enemy when you're doing grinding. Heat is your enemy when you're doing any type of turning or any type of accurate machining. So one of the components of grinding is the size of the coolant tank. When you're doing production grinding, and let's just talk about oil for a second, oil is going to heat up. Oil coolant is going to heat up much more so than water-soluble coolant. So many times what you'll do is you'll want to have the largest coolant tank available for that particular machine, and sometimes that means it has to be higher. So if you see a coolant tank that's higher, that usually means they're trying to get more volume, and it dissipates the heat based on having more coolant. The other thing that should mention about cylindrical grinding is as the oil comes and hits the workpiece and the grinding wheel, as it's spinning, it creates a mist. So on machines that are totally enclosed, many cylindrical grinders are, you'll want to have a mist collector. Once again, our industry is very literal. A mist collector does what? Collects mist, created by the grinding wheel, contacting the oil, vaporizing or creating very small droplets, and you get almost like a haze. So when the operator goes and opens to change a workpiece and opens the door, if you don't have that mist collector, that mist all comes right at the operator's face. Going back years ago, before CNC, you had cylindrical grinders that were manually operated and hydraulically operated, both for OD work and ID work. Many machine tool spindles, the spindle that rotates the workpiece, many of them are manufactured or ground on machines like this. Because if you have a machine that's a universal machine, that means ID and OD, or I should say OD and ID, the relationship on a spindle is critical that you have relationship, very accurate relationship, to the OD of the part or the spindle and the ID of the part or the spindle. And so it all has to be ground at the same time or in the same setting so that the relationships to each other are dead on. One of the things that's important about grinding and turning and other machining operations is that you don't have vibration. Any vibration on the floor or the building can definitely induce surface finish. Surface finish is the smoothness of the part. You'll have variations in the surface finish or lines based on vibration into your foundation. So the bigger a machine is, the more requirement they'll have that the foundation or the floor setting that it's on is solid. Sometimes they'll require that it's a solid pad so many inches thick. But certainly what you don't want is a very accurate cylindrical grinder next to a punch press or next to an open door that in the wintertime in the cold areas of the country, or maybe hot in the hot areas of the country where it's excessively hot. Keeping in mind that thermals in grinding and thermal instability in accurate turning is your enemy. So you want to be a constant temperature. Most grinding equipment is in a environmentally controlled, certainly temperature controlled environment. If you walk into a shop and they have, not necessarily a stable plus or minus 1 degree, plus or minus 2 degree environment, you're going to have variation on your grinding on your parts. Many times in that case, in super precision type machining, when it comes off the machine, it may be a different temperature than when you go into inspection. And you could get size variation just because of that. So that all has to be taken into account when you're doing these type of tolerances. In this particular example, the shaft is held between centers. Sometimes on a lathe you'll hear that between centers, but in this particular case on a grinder you'll definitely hear it. So you'll have a drive plate and a drive dog. Pretty much self-explanatory as well. You'll have many times a dead center on the workhead and a dead center on the footstock or tailstock. So as the workhead rotates the workpiece, that allows you to grind the entire diameter, because once again, it's like a lathe in that regard. But unlike a lathe, the grinding wheel rotates. On a lathe, your turning tool doesn't rotate. It's a single point. Whereas on a grinding wheel, you have a 1 inch or 2 inch wide wheel, which once again is going to generate a lot of heat. One thing I didn't mention earlier is that your workhead many times will need to be adjusted, or on a tailstock you'll have what they call a micro corrector, because you may have taper in a long part that you want to take out. You also many times have the ability on the table itself to set a taper or adjust out a taper. So you'll find on many cylindrical grinders where the table can be adjusted, the tailstock can be adjusted, and in many cases, the workhead can be adjusted to either induce some sort of taper or take some sort of taper out of the part. You also have, in many cases, you can have a follow rest on a grinder for a long, thin part. One of the things I failed to mention is the workhead. Sometimes you'll have the need to do face grinding. So where it wouldn't be a long part like this, where you would take the workhead and you would swivel it 90 degrees. And we'll talk about surface grinding in another video, but when you take the workhead and the workpiece and you rotate it 90 degrees, now you have the face of the wheel facing the face of the part, and you can actually face grind by rotating the workhead 90 degrees. It's another way to use a cylindrical grinder. In this cycle, we're not grinding anything, we're just demonstrating the movements for a grind where the wheel is turning, and you'll see the coolant hose is above the top of the wheel. That would have coolant coming out, either water soluble or oil, and it would be pointed at the point of contact between the part, the workpiece, and the grinding wheel face, so that you would actually have where all the friction and all the heat is going to be generated, the ability to cool that. Earlier I mentioned that you'd have a spark out. So as I'm going in traverse grinding across this shaft, you would actually see sparks, especially when you're doing more of a rough pass versus a finished pass. And then, as I mentioned earlier, when you dwell and you come along, then the sparks will disappear, and that's what they call spark out, and then you would retract your wheel head back to home. When you have a wheel head that has OD wheels or one OD wheel or multiple and ID wheels, that axis is called a B axis. This particular machine has a manual B axis, so it's hydraulically clamped down, and we can unclamp it, so I can, with the wheel not turning, mind you, I can go to the wheel head and rotate the wheel head manually. So if I wanted to plunge grind a certain angle or approach, dress the wheel, and approach to come in and do a grind of a diameter and a shoulder at the same time, that's why you would want to do that. This is the wheel head. And I've unclamped the B axis. And as you can see, I can rotate it so that you have an angle, the wheel at an angle, so you can dress the diameter and the shoulder into the wheel and have an angle approach. Production grinders many times will have a set angle and angle approach, and that's all they'll do is an angle approach, it'll be an angle wheel head grinder. Those are machines that are making thousands and potentially tens of thousands or millions of parts. But this gives you an idea how we can manually position the B axis, which I've unclamped. So the noise you hear in the background is the hydraulic pump holding up the actual wheel head so I can rotate it manually. Underneath, there's a scale that you can rotationally see where you're at. So I've got it lined up at 0, which is now for plunge grinding or traverse grinding. Now I have the B axis clamped. Now the wheel head is sitting down. And there's a coupling, a curved coupling underneath so that it engages accurately. And now I should be ready to continue grinding. This here is the flagging device, and there's such a thing called active flagging, and there's also something called passive flagging. This is active flagging, where it'll come from the wheel head out, and it'll have a probe on the end of it, and then you'll touch off on a shoulder, wherever that shoulder may be, so that the edge of the wheel and the obstruction, or in this case of the shoulder, you're telling the computer where each other are, so to speak. When a grinder gets shipped, a cylindrical grinder gets shipped, many times the shroud is separate from the machine tool, and it's shipped together so that they're joined together. And the first thing that a rigging company does when they put it on the floor is they'll disconnect the bracketry that connects the shroud to the machine tool, to the base. The reason they do that, the manufacturer does that, is that you don't want to induce vibration into the work zone. So any little knock or vibration, if they were connected, would induce variations in your surface finish on your part or tolerance. So many times a machine tool builder of grinding equipment will allow you to ship the machine together, join together with brackets, put it on the floor, and then take the brackets out, which then you have a base, and then the shroud sits separately around it, not physically connected. Once again, really good design, really good concept.